Hello calculus kids, it is time for another video lesson. So in your warm-up book, please write this equation, write this warm-up, find the equation of a line tangent to the hyperbolic branch defined parametrically. Okay, I don't care about any of this blah 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 blah. I care about parametrically, and when I see parametrically, I expect to see x in terms of t and y in terms of t. Remember, we have the Cartesian plane, x comma y, and whatever this curve looks like, where the x direction is defined by secant in terms of time, and the vertical movement and the vertical coordinates are defined by the tangent in terms of time. When I graph that curve on the xy plane, I want to find the equation of the tangent line, which means I've got y and x, so this needs to be dy dx. So to find dy dx, when I have two separate equations, I need to find the derivative of x with respect to time and the derivative of y with respect to time. So what is the derivative of y with respect to time? Is what? Derivative of y is secant squared, right? Of t. And the derivative of x with respect to t is secant t tangent t. This is the coordinate on the xy plane, root 2 comma 1, right, which is 1 something, 1.141, right, comma 1. Whatever this curve looks like, there is a tangent line through this point to the curve when t is equal to 5 over 4. So secant squared t, secant t, tangent t. That slope at pi over 4 goes here. So what is that? Secant of pi over 4 squared over secant of pi over 4 times tangent of pi over 4. Well, tangent of pi over 4 is 1, right? So multiplying by 1 goes away. Secant of pi over 4 squared over secant of pi over 4 is going to just be secant of pi over 4, so this should just be root 2. The x coordinate, the x coordinate is also root 2. And the y coordinate is 1. So the equation of the tangent line looks like that. You can add this to your warm-up. AP is going to test you on parametrized, could test you by giving you the equation in rectangular form, right? You don't see the t in here. This is y is equal to x squared and 7x, right? This is y in terms of x. Y in terms of x. So I can certainly find y prime, can't you? Can't you find dy dx, the derivative of the function y in respect to x? What is that? This is just the power rule, right? 2x plus 7. They want me to evaluate dy dt, not dy dx, at 1. And they're giving me dxdt at 1 is 1/3. So again, thinking about the derivative of y with respect to x and our alternative version of the chain rule, I can tell you what dy dx is at 1 if I find the rule for dy dx. I can tell you that dy dx at 1 is 2 times 1 plus 7, which is 9, correct? Then remembering the chain rule that dy dt, see the chain, be the chain, right? They want me to evaluate dy dt here. So I said, well, dy dt, if I want dy dt, I have dy dx, and I have dx dt, they gave that to me, check. All I have to do is bring down 9 times 1/3. Because my arrow, I gotta put it there, huh? And 9 times 1/3, shocker, is 3. Alright, now in your notes, please title them Implicit Differentiation. Implicit differentiation versus explicit differentiation. This is really just the title of your notes, but I want to explain, I want to backtrack a little bit and say that what you've been doing has been explicit differentiation. Explicit differentiation means that you have a function y explicitly in terms of x, so that when you find the derivative is explicitly in terms of x, right? This was explicit differentiation. Notice that, and let me change the notation here for a minute, the derivative with respect to x of y is explicitly in terms of x. Notice that y equals x squared plus 7x plus 5 is a function, right? Now notice that x squared plus y squared is equal to 1 is not a function. Right? Not a function. And the equation is not explicitly in terms of x, right? In other words, y is not by itself. Here's y wrapped up with x. Now, a circle, I can get an equation, y equals plus or minus the square root of 1 minus x squared, but that's still not a function. I want you to remember Algebra 1 and doing whatever I want to one side of an equation as long as I do the same thing to the other. It's just that this time, what I'm going to do is take the derivative with respect to x of both sides. Every term by term differentiation. That's what this is called. Term by term differentiation. All I'm doing is the same thing to both sides of an equation. Here's my equation. I took the derivative of x squared with respect to x, the derivative of y squared with respect to x, the derivative of 1 with respect to x. Do the same thing to every term on both sides of the equation. Now notice that here the variable that I've never really cared about this, the derivative with respect to x of x squared, everything is good. The derivative with respect to x of a constant, everything's good. But the derivative of x with respect to a variable that doesn't match, oh no, I don't know what to do. This is where we have to remember the chain rule. I want you to cover up the y since the variable does not match, right? Variable matches. Everything's cool. Variable matches. I need you to imagine there is an x to the 0 there. Everything matches. Cool. The x, the variable of differentiation, does not match the variable here. That means I need the chain rule. So, differentiate x squared normally. So I'm going to differentiate, what is the derivative of x squared? 2x. What's the derivative of the constant 1? 0. However, what is the derivative of stuff squared? Remember this from yesterday? The derivative of stuff, from Friday, the derivative of stuff squared is bring the 2 down, copy the stuff over, subtract 1 from the exponent, and spit out the derivative with respect to x of the stuff. So, what does that look like when my stuff is y? Right? The derivative of x squared is 2x. The derivative of the constant 1 is 0. What is the derivative of the stuff squared? Bring the 2 down in front, copy over the stuff, subtract 1 from the exponent, spit out the derivative of the stuff with respect to x. Now my goal is to get dy dx by itself. So I'm going to do algebra 1. Move the 2x over to the other side. Divide by 2y. Simplify. This equation generates all the slopes on my circle, even though my circle is not a function. Now notice that the slopes on my circle involve both the x and the y coordinate. That's never happened before. Right? That's never happened before. Our derivative functions have all been explicitly in terms of x. The y coordinate has not mattered. Right? And that's why the whole vertical shift issue, right? The function, the derivative of x squared, 2x, is the same as x squared plus 1 or x squared minus 2. But notice here, the derivative, the slopes on my circle, are the negative ratios of the x coordinate to y coordinate. So check out this point on the circle. X squared plus y squared was equal to 1. Shocker, the unit circle, where you have 0.5 comma root 3 over 2. Right? That shouldn't surprise you. 1/2 root 3 over 2. What is the equation, or what is the slope of the tangent line there? The slope of the tangent line, this slope is the opposite of the x coordinate, which is 1/2, to the y coordinate, which is root 3 over 2, which of course is 1 over root 3. What do you think that angle is? Math is so cool. How about this? What do you think about that point? That point is negative 0.5, negative root 3 over 2, right? In the third quadrant, the slope of that, oops, I forgot my negative out here. The slope of this tangent is negative 1 over root 3. Crazy. Now notice this equation, the equation of the circle, I could solve for y. This would be disastrous to solve for y. It would involve inverse sine and blah 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 blah. Check out the use of implicit differentiation, because x and y are all mixed up together. I need implicit differentiation. Oops, sorry. Implicit differentiation. You cannot explicitly get a derivative if you can't explicitly solve for y. So I'm going to use this equation sign, and I'm going to take the derivative of every term with respect to the same variable. Take the derivative with respect to x, take the derivative with respect to x, take the derivative with respect to x. Figure out where you need the chain rule. Where you need the chain rule is where the variables don't match. The derivative with respect to x of y, those don't match. I'm going to need the chain rule. The derivative with respect to x of x squared, no chain rule necessary here. The derivative with respect to x of y, those variables don't match. I'm going to need the chain rule. So this confuses kids sometimes. Remember, this is stuff to the first. So what does the chain rule look like? Bring the 1 down and multiply times 2. Copy the stuff over and subtract 1 from the exponent. So that's 2y to the 0. Spit out the derivative of y. But of course y to the 0 is just 1, which is why you don't see it. The derivative with respect to x of x squared is just 2x. Check. The derivative of sine of stuff is differentiate sine, cosine. Copy over the stuff, spit out the derivative of the stuff. Now do algebra 1. Collect like terms. Get your dy dx's together. So I subtracted cosine y dy dx from the right side. Now, good F word, factor dy dx out of the left side. Now divide to get dy dx by itself. Notice that when I have dy dx, I'm going to have both an x and a y in my derivative rule. Implicit differentiation means my derivative has both x and y in it. The derivative, the slopes, depend on both coordinates. So So again, this technique is called implicit differentiation. Step 1. Well, really the prequel step to this, the prequel is recognize. You need to recognize that you need implicit differentiation. How you recognize the need for implicit is that the x's and y's are all mixed up together. You don't have y equals x stuff. Then you differentiate both sides. WRT is with respect to the same variable x. And you're always looking for the chain rule when your variable of differentiation does not match the variable in the equation. And then you use algebra 1 and get dy dx by itself. So maybe pause the video and see if you can do this problem by itself. But let me give you a warning that the middle term is a product. Okay, welcome back. So, to find the derivative of x squared minus xy plus y squared is equal to 7, which is not a function. X's and y's are mixed up together. I recognize the need for implicit. I need implicit because my x's and y's are mixed up together. There's no y by itself. No y equals x stuff. Therefore, I need implicit. So I am going to do term by term differentiation. I notice that I've got y's, so I am going to take the derivative with respect to x of x squared and get 2x. Here's my minus sign, and I put a bracket here because I need the product rule between x and y. The product rule never changes. The first function times the derivative of the second function plus the second function times what? What's missing here? That's right, the derivative of x with respect to x, which is just 1. So that's y times 1. Plus, how do you differentiate stuff squared? This is stuff squared. How do you differentiate that? You bring down the 2, you copy over the y, you subtract 1 from the exponent, and then to get a 1, and then you spit out the derivative of y with respect to x. And don't forget, you must take the derivative of this constant. The derivative of 7, technically x to the 0, is 0. Now it's time. Calculus is done. It's time for algebra. I distributed my negative sign. I'm going to get my dy dx's on one side and my other crap on the other side. Then I'm going to factor the dy dx out, and then I'm going to divide. The derivative of y with respect to x involves both coordinates. The slopes on this curve, which is not a function, depend on both the y and the x coordinates. I could further ask you or I did ask you to write the equations of the tangent line, right? I almost forgot. I was so involved in doing implicit differentiation, the product rule, and the power down rule with the chain rule, that I forgot that they asked me to find the equations of the line tangent and normal. So slope and perpendicular slope. So I plug in 2 for the y coordinate minus 2 times the x coordinate, 2 times the y coordinate minus the x coordinate. So the slope of the curve at negative 2, 1 is 4/5. So there is the equation of the tangent line. And if somebody makes you clean it up into mx plus b, but not necessary, the equation of the normal line, clean it up into mx plus b only if asked, or you're matching multiple choice. This is a bit of a dagger. Higher order derivatives are not a really big deal in explicit differentiation. But in implicit differentiation, this is a bit of a dagger. Sorry. So, find the second derivative if the original curve is 2x cubed minus 3y squared is equal to 7. Notice again, x's and y's are mixed up together. Getting y by itself would mean a plus minus square root thing. That's an even bigger dagger. So the first thing I do to find the second derivative, obvi, I need the first derivative first. I identify where I'm going to have to use the chain rule, wherever my variable does not match the variable of differentiation. Now I'm about tired of writing dy dx all the time. So notice that this time I kind of cheated. I took the derivative, well, I didn't cheat, I just used different notation. I took the derivative with respect to x of 2x cubed. That's just bring the 3 down, multiply times the 2, x, subtract 1 from the exponent. Done. Minus the derivative with respect to x of 3y squared. Now I'm going to have to use the chain rule, right? So I'm going to bring the 2 down and multiply times the 3. Copy over the y, subtract 1 from the exponent, spit out the derivative of y with respect to x. Notice I just wrote y prime instead of dy dx. Don't forget that you need to take the derivative of the constant to get this 0. What you do to one side of the equation, you must do to the other. If you're going to take the derivative of 2x cubed and you're going to take the derivative of 3y squared, you best take the derivative of 7. Now you want to get y prime by itself. So subtract 6x squared and divide by negative 6y. Cancel out the negative 6's. And the first derivative is a quotient. What does that mean? To find the quotient rule, what are you going to have to do? If your first derivative is a quotient and you need to find the second derivative, dagger, you're going to need the quotient rule. What the hee-haw is that? Copy that down while we think about it for a second. To take the derivative of a quotient, right? This is high over ho. So the second derivative is ho times the derivative of x squared minus high times the derivative of y. What is the derivative of y? It's y prime. All over ho squared. So that's y squared. You have found the second derivative. you get almost full credit. You get, from a problem starting here, having to get all the way through the first derivative, then do the quotient rule, and get the second derivative, you get almost full credit. The reason you don't get full credit is because although the first derivative, because of implicit differentiation, must be left in terms of y, and you don't have a rule for y, so you can't replace this y, in the second derivative, you also have y, and you have no explicit rule for y. You cannot replace these y's. However, look at this purple box. You do have an explicit expression for the first derivative. It's right here. You must replace. So let me do some elementary school math here. Isn't it true that, let's say, 7 minus 5 over 2 is 7 over 2 minus 5 over 2? Isn't that true? So if that's true, watch what I'm going to do with this second derivative expression. I gave the denominator y squared to y times 2x over y squared, and then canceled a y to the first, leaving me with 2x over y, minus x squared y prime over y squared. Right? Technically the y prime is over 1, right? So y prime is 2x minus y minus x squared over y squared times y prime, but y prime is x squared over y, and that's what I put there. OMG. You could get a common denominator, you could square, you could multiply top and bottom here by y squared if you want. If you really wanted, you could write this as all over y cubed, multiply this by y squared over y squared, and get 2xy squared. Right? This answer is perfectly appropriate too, but you don't have to. You can leave it just like this if you wish. But the important thing for higher order derivatives, for implicit higher order derivatives, okay for y to be in your derivative. But not okay to have y prime in the derivative rule. You must. Now again, you're going to get almost full credit. That's a -1 or a -1/2 if you stop here. And of course, if this is a multiple choice question, you're not going to see this. You're either going to see this answer or this answer. Alright, so that's it for implicit differentiation. Please do homework number 2 on your pink sheet, or from the warm-up slide all the way at the beginning. And I will check Friday's homework, which is the chain rule homework, and implicit differentiation homework from this lesson all tomorrow. Hope you had a good weekend and have a good afternoon, and I will see you tomorrow.